Hi there everybody, welcome back to another Chem Complete video, and in today's video we are going to take a look at how to interpret organic skeletal structures. So one of the things that students have to come to grips with when they get into organic chemistry or any course that uses organic chemistry is how to look at these line bond structures that start coming up and how to read them and interpret them to determine the organic information that's being given from that structure. So that's what we are going to take a look at on the channel, and that's coming up right now. Okay, thank you so much for joining me today and using Chem Complete for your chemistry needs. A brief reminder before we get started here, there are a lot of free resources over at chemcomplete.com. You can sign up and take advantage of that. There's also guides that are available for sale. Only a couple of dollars. It's a great way to support the channel, and it gives you a very detailed walkthrough, more detailed than I can go through in a lot of these videos. So with all that said, let's go ahead and get started. Okay, so there are three major ways that we can express organic compounds when we start looking at organic structures. Now, the first one is the one I would expect most people coming out of a general chemistry course are used to, and that is traditional Lewis structures. So this is going to be where you're drawing out each individual atom. You're showing every single covalent bond with a line that is drawn between those atoms, and then you fill in every single lone pair that potentially could be there. So traditional Lewis structures are the ones that most students are familiar with as soon as they're setting foot in a classroom where organic chemistry is needed. Now the next one I call condensed structures. So this is going to be a situation that's somewhere in between the line bond format as well as the traditional Lewis structures. The biggest key here, and I have this stated, is that you're going to start chunking your hydrocarbons, okay? So for instance, if I have a traditional Lewis structure, I could say that I've got a CH3 attached to another carbon, and it would look like this. I'd have the 3 hydrogens and then another carbon, right? And then let's say that this is a CH2, and then let's say that this is a CH3 again, right? So this is propane, the gas that you would normally grill with. That's the structure of propane. Now it's drawn out there in its full Lewis format. The condensed structure would take all of these hydrogen bonds and just chunk them together with the carbon. So in this type of scenario, I would have CH3, I draw a line, then I have CH2, and then I draw a line and I have CH3. And in fact, many times organic chemists will start eliminating the lines. So they'll just put CH3, CH2, CH3. Okay, this is the condensed form. And one of the things that you want to realize is that when you've got these forms, generally speaking, 99% of the time, the carbons are going to be bonded to the next carbon in line. And then whatever comes after that carbon is the material that is surrounding that particular carbon, right? So when we deal with organic chemistry, we deal with these carbon backbones where you've got carbon, 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 they kind of chain together. And then around the periphery of that carbon backbone are your hydrogens, nitrogens, oxygens, and they couple together to make different functional groups, and those functional groups have different reactivities. So the last way that we can express this is through skeletal structures, which we sometimes call line bond structures because we just use lines to represent the carbon-carbon bonds. So the example of the skeletal structure for propane would just be this. Now obviously, if you were to come in and set foot in a classroom and you had not been exposed to this, you would look at this and think you were in a geometry class or something of that nature. Well, the way that we interpret this is that each one of these points is going to be considered a carbon, and unless something else is shown on these points, then you are going to have hydrogens that you just assume are there, right? So if I have this carbon, I would assume there's 3 hydrogens present here, and then I take my 4th bond over to the CH2 in the middle. This carbon would have 2 hydrogens because it's got 2 other bonds to carbons, and then this CH3 on the right to finish. So this is the skeletal or the line bond structure. Now, skeletal structures become more important the more complex the molecule becomes. Because as you continue to rack up carbons in your molecule, it gets very cumbersome and burdensome to draw out each individual carbon, particularly if you're going with the traditional Lewis structure format, because then you're drawing out every single hydrogen associated with that carbon. It starts to take up a lot of room, and it starts to become just not as efficient in terms of expressing the structures. Okay, so let's take a look at a couple of examples here. What we're going to do is we're going to look at each of these in all three formats so that you can kind of translate from one to the next. And we'll start with the traditional. We'll go with the Lewis structures, then we'll put those into condensed structures, and then those condensed structures will turn into the line bond structures at the end, so you can get a variety and see what's going on here. Okay, so to start, let's take a look at ethanol. So ethanol is a simple alcohol. It's actually the drinking alcohol that most people are familiar with, that would be in spirits or beer or that kind of stuff. So going with the traditional Lewis structure here, what I would expect for ethanol is CH3, CH2, an O, and then a hydrogen. So there's the official Lewis structure for ethanol. Okay. For acetone, it's going to be, now I'm going to give some space just so it doesn't collide too much with the ethanol here. Okay, a CH3, a carbon that's got a double bond to an oxygen. That oxygen would have 2 lone pairs. And then a carbon, 3 hydrogens on the other end. So there's the proper Lewis structure, okay, for acetone. And now for octane, this one is where you're going to start to see it becomes more and more acceptable or desired to use the abbreviated versions. So octane, the root oct there is 8, so this is going to be an 8-chained hydrocarbon. So what we'll do, let's make the initial carbon chain, and then we'll move from there. So I'm going to need 1, 2, 3, 4, 5, 6, 7, 8. Okay, so then I'm going to draw each of these. Now the terminal carbons, and when we say terminal in organic chemistry, it means whatever the chain is ending with. It's the terminus of the chain, would have 3 hydrogens, and all the others inside would have 2 because they share 2 bonds to the neighboring carbons, right? So it doesn't really matter. Sometimes you can put them here on top and then on the bottom and alternate like that. Okay, if you're trying to show a more tetrahedral type geometry. So CH2, CH2. Now look at how large this molecule is and how, I don't know what the right word would be, how annoying it is to write it out, how much space it takes up, how crowded it is. Okay, and octane can still be considered a relatively small organic molecule compared to some of the larger structures that are out there. Okay, so you can see the Lewis structures here. This is where you would come from in a general chemistry sense. So if you were to set foot in the door and your teacher or professor were to give you these structures, this is how you would initially probably attempt them coming out of a general chemistry class. Okay, so let's move to the condensed structures for ethanol, acetone, and octane. It's going to make our life a little bit easier here. So now we've got for ethanol, CH3, I don't have to draw those bonds out, CH2, and then I've got an OH at the end, right? So that would be for ethanol. For the acetone, I would have CH3. Now you could write C with an O and then another CH3. I typically, if I have a specialized functional group like a carbonyl, I'll still draw that out to show it separate there. So that's the way that I would prefer to show a condensed structure. But if you wanted to, you technically could show it this way, where you'd say CH3, CO, CH3. Okay, you have to be comfortable reading this as an organic chemist and realizing that this technically belongs to that for the Lewis structure to make sense, okay? Because if you were trying to take it out some other way, let's say that you said, okay, so that's CH3, and then carbon, and then oxygen, and then CH3. Okay, well, that oxygen would have lone pairs here, okay? Same with this one. Being a true organic chemist and starting to forget to show my lone pairs because I only care about them if they're there in reactions. But if you take a look, this carbon only has 4 bonds and nothing else, I'm sorry, 2 bonds, 4 electrons, and nothing else that it can grab onto. So that's not a valid Lewis structure. You have to make sure that you're creating valid valence electron sets around your compounds, okay? And then finally, for the octane, it should be easier to write this time. We just have to keep count of our carbons. So CH3, so that's going to be 2, 3, 4, 5, 6, 7, and then remember for 8 you need to be at a terminal again, so you'd have a CH3. Okay. A lot of organic chemists would also write it this way, and this is acceptable. You can say CH3, in parentheses you can say CH2, and then clarify how many you want. So I would want 6 of them, because the 2 terminals would then give me a total of 8. So this is another way that would be acceptable for writing a very condensed formula for octane. Okay? Now for the skeletal structures. So this is the payoff. This is supposed to be the most simplistic part. And then I've got one other note about cyclic systems, because most students don't see compounds that form cyclic systems or rings when they're in general chemistry, and then this concept comes up in organic chemistry. It can start to get confusing. And so skeletal structures are kind of most useful, even though they have great use overall. They're most useful when you start talking about ring systems, okay, in terms of being able to quickly draw them out without having to draw all the individual bonds there. So skeletal structure for ethanol would be 1, and that second point is 2, and then when I come down, I have the OH here. Now notice I can't just stop at that point and not show the OH and have the user infer that it's an OH, because if I did this, well, that would then tell the user this is a CH3, right? Like we saw before with propane. So I have to specify to the user, or to the, I should say to the reader, right? The person that's looking at it, hey, this is not a CH3, this is going to be an OH group. So if it's not a CH group or a hydrocarbon group, then we have to specify it in the line bond structure. You can't just draw a bunch of lines and have them fill in the blanks. Okay, so this would be CH3, CH2, OH. For acetone, I know that I have 3 carbons, the CH3s are on the side, and then I've got a double bond to an oxygen here. Okay, and again, sorry that I'm forgetting the lone pairs. That's a force of habit when I'm drawing organic structures. I typically only show the lone pairs if they're going to get involved in a reaction as far as donating or receiving. Okay, so there's acetone. And then finally, now you have to keep count here, okay, for octane. So you've got 1, 2, 3, 4, 5, 6, 7, 8. Now when I do this, I always encourage students to go back and double check, especially the longer the chain gets. So make sure you've got 1, 2, 3, 4, 5, 6, 7, 8. We do. There's a total of 8 points along this kind of peak and valley structure. And so this would be the correct form for octane. Octane does not have any oxygens, nitrogens, other additional functional groups, and so that's the structure that I would expect there. That's how I would interpret that. Okay, now cyclic systems. So when you get into organic chemistry, a lot of times organic chemistry, even if you see, images of it posted before you've ever taken it, you'll see these ring systems, right? These giant ring systems that are kind of enclosed, and then they have a bunch of stuff branching off of them. I feel like that's one of the iconic visualizations of organic chemistry. So cyclic systems utilize, okay, these points around the ring. So a cyclo, meaning cyclic, pentane is 5, you're going to have a 5-membered ring. Okay, so this is the way organic chemists will usually show cyclopentane. It is possible that you could show it this way, although it starts to become, again, a little burdensome to constantly draw it out this way. Not that you couldn't. Okay, CH2. And then finally, you would want to come up, CH2, like that. Okay, and you can imagine if you're doing the proper Lewis structure, you have to draw the carbon ring, right? And then after the carbon ring, you have to show each of the individual hydrogens that are coming off of that. So again, for a 5-membered ring system, it may not be that bad to you, but you can see how, I don't know if ugly is the right word, but how clustered and how much space and confusion kind of can quickly take up room on your drawing here. Okay, so this is going to be the way you would see cyclopentane represented in organic chemistry 99% of the time. Benzene is another common one. So a lot of people have seen this structure where you've got a 6-membered ring and then you've got these alternating carbon double bonds. Okay, so if I were to draw that out properly, it would be that I've got something of this nature. And you can see that, again, the closer I go towards condensed structures and then formal Lewis structures, the more material is kind of in a small space here that is starting to crowd up, and it becomes, actually, I would argue, more difficult to read than simplistic to read when you're looking at those points. Okay, so I think that about wraps it up as far as how to read the different compounds in organic chemistry. So remember to like the video if it helps, subscribe if you want to stay up to date throughout your chemistry classes and your chemistry career, and I will continue to release new updates. Thank you so much for learning with me. One more shout out to chemcomplete.com, and I will see you guys in the next episode.